basically what we're going to be talking about on today. But it's just going to be a little bit simpler, putting it more so in words than dealing with the actual formulas themselves. So in the textbook, it actually gives us the definition, word definition for the general formula for a linear function or a linear model. And it is considered to be our dependent variable is equal to the initial value plus the rate of change times the independent variable. Now, basically the difference between an independent and dependent variable, the dependent needs the independent variable in order for it to exist. So that's the way we're really going to actually look at it. If the independent variable is not there, then that lets us know that the dependent variable does not exist. And again, the rate of change is the change in the independent variable divided by the change in the change in the dependent variable divided by the change in the independent variable. And from a mathematical perspective, that is known as our slope. So again, when we say the rate of change, we are considering it to be our slope. And if you recall from a given coordinate, we remember that my slope is y sub 2 minus y1 over x sub 2 minus x sub 1. So these are this is the information that we really need to know in order to process through this particular section. And there is one more, which is our slope intercept form, which is y is equal to mx plus b. Y is equal to mx plus b. Again, where m is our slope and 0b is the y intercept. 0b becomes the y-intercept. And this is something that we should be familiar with from an algebra class. This is just what I have read. It's basically what we're used to seeing. What's in black is just a wordy version of what the information that is in red. So this is where what we're going to be talking about and discussing on today. I will give you about another minute or so to finish copying it if need be, and then we will move on. You can find me in your textbooks. I'm going to be on page 557 in your textbooks, and I'm going to be looking at number 12. Page 557, number 12 in your textbook. All right. Now, again, page 557, and we're looking at number 12. There are three parts that we want to actually deal with. The first part is we want to basically consider the following graphs. Part A, in words, describe the function shown on the graph. Part B, find the slope of the line in the graph and express it as a rate of change. Be sure to include the units. And C, briefly discuss the conditions under which a linear function is a realistic model for the given situation. So again, I'm going to quickly sketch what the graph is that we have again for number 12. And this here is our graph for number 12.
What page are we on again?
This is on page 557. So again, this here is a basic idea of what the graph is. And again, you can actually look in your textbook to get a much cleaner picture of this. But we know, again, the textbook tells us that the horizontal axis is in terms of time. And this is in hours. And my vertical axis deal with the population. And this is in terms of thousands. So again, the horizontal axis is in terms of time, vertical axis in terms of our population. So when we look at part A, we are going to say from this angle, the independent variable, or as the independent variable, and my independent variable in this case is considered to be time, increases, the dependent variable which is considered to be the population, increases as well. So again, as my independent variable time increase, the population actually also increases. So this is going to be the written words of the description of this graph. So as my X value increase, my Y value is increased. Part B, they want to state what my slope is. And remember, my slope is M is equal to Y2 minus Y1 over X2 minus X1. So that means we would need to find 2 points. And the 2 points that I am going to actually work with, 0, 0, which is the origin, and the first point, which is here, which is 2 and 20. That's going to be the second point that I'm going to be utilizing. So we already have stated M is equal to Y2 minus Y1 over X2 minus X1. So again, remember, the second set of points are the sub 2s. The first set of points are the sub 1s. So we end up with 20 minus 0 over 2 minus 0, which gives me 20 over 2, which gives me the value of 10. And the units will be in terms of thousands per year. So this is basically 10,000 per year. That's how much there's going to be a change. A year, it should be an increase of 10,000 per year. Any questions? Any questions? And then the last piece, letter C. We're going to say something like this, and it's kind of going to almost echo what we said in part A. Population grows consistently over an 8-year period. Now, how do I know I'm dealing with 8 years? Because it starts at 0 and the graph actually ends at 8 when my X value is equal to 8. So again, population increases constantly over 10 years, over the 10-year period. Let me, running out of room, so I need to move this over a little bit. So again, latter part, just trying to give some type of verbal explanation or description of what this graph is actually saying. The population grows constantly over a 8-year period. Are there any questions? Are there any questions? So basically what we are trying to do, what this section is trying to do, is get you to see the relevancy of how linear models and being able to describe them from a day-to-day perspective. Any questions? Okay. If not, we're going to look at our next example, and that is going to be number 13. We're looking at number 13. So again, I am going to actually draw this graph, and then we're going to address the questions. So with number 13, we have the following. Let's call this 100, 500, 1,000, and 1, 2, 3, 4, 5, 6, 7. And we have a line such as this. This here is our graph that we actually have. Now, notice something, looking at the first graph that we have in reference to the second, compared to the second graph that we have. First graph, if we read from left to right, it was going up, so my slope is going to be positive. This current graph, if we read it from left to right, it is going down, so my slope should be negative. So just by looking at the picture, you should be able to tell me the sign of my slope either being positive or either being negative. And again, looking at it from left to right, the direction will tell me the sign of my slope. So let us look at part A. Now with part A, we are going to look at the independent variable and dependent variable in reference to our graph. And as the independent variable, and my independent variable here is time. Independent variable is time. Increases the dependent variable, which is my distance, decreases. So as the horizontal axis gets larger and larger, remember this here, horizontal is time, where the vertical is my distance. So as time grows, my distance gets smaller. As time grows, my distance actually shrinks and gets smaller. So let us look at part B. They want us to compute my slope. Now remember, my slope, we're gonna have to have 2 points. And the 2 points that we know for sure is 0 and 500, along with 7 and 0. So those are the points that we're going to use in order to calculate what the slopes are. We really cannot justify or tell by the picture any other points for sure. So we want to have good points here. So again, 0, 500, along with 7 and 0. So we end up with M is equal to 0 minus 500 over 7 minus 0, which gives me a negative 500 over 7. If we round this guy to the first decimal, we end up with a negative 71.4 miles per hour. And this is the slope that we actually have. For every 1 hour, we know that the distance is going to decrease at the rate of 71.4 miles. That's basically what the interpretation is. And last but not least, letter C, we're going to look at how this is going to the wordy part. And that's basically what I'm looking at, the wordy part. So C, you will say distance decreases constantly over a 7-hour period. Questions, comments, concerns? Questions? Questions? All right. If not, we are moving on and we're moving on to number 23. We're looking at number 23. And with number 23, we have the following. The following situations can be modeled by linear functions. In each case, write a equation for the linear function and use the answer to, use it to answer the given question. Be sure to clearly identify the independent and dependent variables, then briefly discuss whether a linear model is reasonable for the situation described. For the most part, it is going to kind of work out, so we will not have to worry about that last part. So with number 23, we have following. The price of a particular model of car is $18,000 today and rises with time at a constant rate of $900 per year. How much will a new car of this type cost in 3.5 years? All right. So first of all, define my variables. So we're going to call this T, which is our independent variable, which stands for our time. Then we're going to have C, which is our dependent variable, which will actually stand for our costs. So if we go back to the very first page that we actually had, we can say it from this angle. The dependent variable, which is denoted as C, is equal to the initial value. The initial value that the word problem gave us was $18,000 plus the rate of change. Now, what is being changed? Every year, the car increase in value by $900. So 900 is going to be the actual rate of change times the independent variable, which happens to be T. So C is equal to 18,000 plus 900 C. Remember, we actually wrote it a little backwards, meaning 900 C plus 18,000. So either way, it is fine. It doesn't matter. So now that we have our equation, part B, we can actually go and identify or solve for C, because we want to know how much it costs. They gave us what time was, which is 3.5. So we have C is equal to 18,000 plus 900 times 3.5. Rounded, well, if you do the calculations, no rounding needed, we end up with $21,150. Are there any questions? Are there any questions? Okay. Again, all we're doing is just initiating and verifying or reporting what my variables are, which one's independent, dependent, and then find my equation, answer the question. Number 25. Thank you. Gotcha. 25, we have the following. A snowplow has a maximum speed of 40 miles per hour on a dry highway. Its maximum speed decreases by 1.1 mile per hour for every inch of snow on the highway. According to this model, at what snow depth will the plow be unable to move? So again, going to define some variables. So we're going to have D to actually deal with the independent variable. And this is going to stand for the depth. Now, ladies and gentlemen, these variables, you don't have to use the exact variables. I'm just using D because it talks about depth. And S we use for the next variable because it talks about speed. But if you want to use X and Y, it's perfectly fine. Just to find them so we know what we're talking about if someone else looks at your work. So again, S is going to be the dependent variable. And this is going to be defined as our speed. So with that being said, my independent variable, which is S, is equal to the rate of change. It says it is slowing down at 1.1 miles per hour. So because it's slowing down, it becomes negative. So it's a negative 1.1 times your independent variable, which happens to be D, plus the initial. Now, what is my initial? My initial is going to be 40, because on dry ground, we can run 40 miles per hour. And again, ladies and gentlemen, please forgive me. I just wrote this in reverse order. If you feel comfortable putting 40 minus 1.1 D, that's fine also. Either way works. Either way works. Any question on my equation here? Any questions? All right. If not, then we are going to deal with part B. Part B, we want to know what is going to be the snow depth when the vehicle stops moving. So my speed in this case, S, is going to be 0. So we're looking at 0 is equal to a negative 1.1 D plus 40. This is why it is so important that you define what your variables are. So when you're trying to address the question, you know what is given. Is it the S or is it the D? So if we solve for D, ladies and gentlemen, we have a negative 40 is equal to a negative 1.1 D. So D ends up being the value of 36.4 inches. And again, this 36.4 has been rounded, Any questions? Any questions? Comments, concerns? All right. If not, I would like for you to do number 28. And we're doing the same exact thing. We are going to, first of all, define what my variables are. After we define what the variables are, create your equation, and then answer the question. So, number 28. I'll give you a few minutes to work it out. All right, ladies and gentlemen, again, depending on the variables, if you use P and T, that's fine. If you use other variables, that's also fine. But your P, which is our population, is the dependent variable, well, T is the independent variable. So you should have came up with something of this nature. E is equal to 250 T plus 1650. And the population in 2030 will actually be 6,650 people. 6,650 people. Are there any questions? Any questions? Any questions? All right. If not, we're going to move on to the last part of this, and this is dealing with graphing. Given a linear equation, they want us to be able to graph our linear equation. So let us look at number 36. We're given the following equation. Y is equal to a negative 3x plus 3. And with number 36, they want us to do the following. We want to find the slope of the graph and the intercept. And when I talk about the intercept, we are referring to the y-intercept, that value of b. And Then we want to sketch the graph for the values of X between -10 and 10. What I am going to do is as follows. The best thing to do is to plot these points, find out the actual coordinate for X is equal to -10 and then 10. And we will already have our y-intercept. Just hit those 3 points, plot those points, connect the dots, you'll be good. So when X is equal to a -10, we substitute -10 every time we see an X, we can actually solve for Y. -10 times -3 is a positive 30, plus 3 gives me 33. And then 10, X is equal to 10 times a -3, -30 plus 3 gives me a -27. So I see that my ending points are -10, 33, and 10 and -27. Also, you should see that M, which is our slope, is equal to a -3, and B gives me a 3. So this lets me know that my y-intercept is equal to 0, 3. So let's look at what my graph is going to look like for this particular equation. Here is -10. Here is 10, -27. Here is 33. So we will have something like this. That first point. Here is the y-intercept. Here is the final point. I know my line is crooked, but y'all should have a straight edge to actually work yours out. So again, this is just what we needed. This is the line in between -10 and 10, and we've determined where it actually crosses the y-axis. And that's it. Try this one more time. Kept it the way it was the first time. All right. Any questions? Any questions? And notice this, slope is negative, so my line should be going down. So everything actually fits together. This always is the case. Slope is negative, line is going down. If slope is positive, the line will be actually going up. Any questions? Any questions? All right. If not, I need for you to do number 38, doing the same thing. I need for you to actually state what my slope and the y-intercept is, and then graph these points when X is equal to -10 and +10 to get that those Y values. So you can actually generate those other 2 points, plot those 3 points, connect the dots, and that'll be it. So again, number 38. Need for you to do number 38. Ladies and gentlemen, you should have something of this nature. Again, your graph hopefully looks a little bit better than mine. But hopefully you get the gist of it. Are there any questions? Any questions?